Good afternoon, everybody. My name is Pat Iampietro. I'm the Geospatial Technology Officer at California State University, Monterey Bay. And this afternoon's session is high precision mapping. I hope you guys are all having a great drone camp. And hopefully today we'll be able to cover some material that will help you in your mapping pursuits to produce higher precision, more accurate, and more repeatable results and data. A little outline of the talk today. First, we're going to talk about why precision is important and reasons why we might want to increase the precision of our mapping products. We'll talk a little bit about how GPS works, because by and large, most of the methods that we have for making more precise maps are dependent on GPS. Maybe a little bit about the difference between accuracy and precision and how those terms are relevant to our work. And then a little bit of methodology and sort of equipment roundup regarding methods to improve precision in our drone mapping projects. So why do we need high precision? It's pretty amazing that the structure from motion technology and the software that we use for our stitching, our photogrammetry software, can actually produce very internally consistent orthomosaics, 3D point clouds, and models without GPS, without ground control points, with known positions, and even without positions for the images themselves. You can take a collection of pictures with your mobile phone that are overlapping, overlap is the real key there, that are highly overlapping of just about any object, and dump them into Pix4D or Metashape or any other good photogrammetry software, and it will create a model of from the data. It will lack real world coordinates, it will lack scale, it may have strange orientation, and in some cases it may be distorted a little bit, but it actually, the fact that the software relies on automatically created tie points from identified pixels in overlapping images, and it creates thousands of those tie points, it can actually make a very internally consistent 3D model from images that have no position at all. But we want to reference our mapping products to the real world. And in a lot of cases, what we want to do is we want repeatability. And we want to be able to go out and potentially detect change. And so if we're going to need to compare maps that were made now to maps that were made, say, a year ago or at some other time, and detect whether things have changed, we need to have high confidence that any movement or change that we see is not due to uncertainty in our models, but is due to real change. So one of the main reasons we want high precision is to detect change. We also often want to just have high confidence that we can compare our results with those from other data sets or those from other providers. We want to be able to share our data, and we want it referenced to real world coordinates with high confidence so that we can be sure that, that when things are compared, they will line up as they should. And accomplishing this sort of higher precision takes a little bit of extra effort. It's a little harder than just going out and flying your drone and taking a bunch of pictures and coming back and processing the data. So the bulk, or actually all of what I'm going to say today, is going to address using GPS to improve the precision of our mapping efforts. There are other ways to do this. There are optical methods, there are surveying methods like using a total station. There are many ways to get high confidence positions for objects in the real world. I'm going to concentrate on the one that I know the most about, which is using GPS. So that's my disclaimer for the beginning here. My other disclaimer is I am not a licensed surveyor. I have used high precision GPS equipment in mapping for over 20 years and have a fairly good understanding of how it works, but I am not a licensed surveyor. And so any questions about the legalities of licensing and surveying, I would have to defer to somebody who knows better. So GPS, and more properly, the term should be GNSS, which stands for Global Navigation Satellite System. Devices are ubiquitous now. They're everywhere. Everything we do seems like has some kind of GPS attached to it, or telling us where we are in our cars, with our phones, everywhere. The technology has become miniaturized. It has become very affordable. The chips that accomplish this amazing feat of telling us where we are on the globe have shrunk down to very small, and everything has GPS now. But the capabilities of those devices vary quite a bit. While your mobile phone may be able to give you a position, and some people actually use mobile phones for mapping with applications like ArcGIS Collector to store features and so forth. A mobile phone may be able to give you a position that's a few meters accurate. And the GPS sensors in your drone are a little better than that, but they're still only going to be good to a few meters. What you really need to improve the precision of your mapping products is a dedicated unit that has some sort of differential GPS capability, and I'm going to explain what that means. WAS, or satellite-based corrections, can narrow the position of a GPS unit down to a meter or two, or in some cases, maybe as good as a half a meter. And that's where we're going to start to see improvements in our mapping products when we can locate our GCPs to that sort of accuracy. But if we want to really nail things down, we want sub-meter precision. And in order to accomplish that, really generally, either real-time kinematic or post-process kinematic, these are both kinds of differential GPS. Those kinds of techniques are really what's needed. So we've got this amazing technology called GPS, and let's just look really quickly, hopefully it's quickly, it might not seem quickly, at how it works. We've got a constellation of satellites orbiting around the Earth, and there are, at any given time, in terms of the ones that are turned on and working, 25-ish satellites. We're on our second generation of Navstar satellites, and a new third generation is just going up now, as a matter of fact, which is going to improve things even more. But the point is that there's a constellation of satellites orbiting around the Earth, and at any point on the Earth, the number of satellites that are visible to you varies throughout the day. Each satellite orbits the Earth about twice every day, and so on any given day, you can see a collection of satellites that happen to be overhead at the time that you are trying to use your GPS. But it's important that you have more satellites and that they're in the best orientation possible for you to get the best possible results. There are other constellations of satellites orbiting the Earth. The European Union has one called Galileo. China has one that's not on this figure, called Beidou. There's GLONASS is a Russian system. And the better, they all are in high Earth orbit to give better coverage and for the satellites to survive for longer. And if you have a decent GPS, the better GPS units can use more than just the United States GPS Navstar satellites. They may be able to use GLONASS and or Galileo. And this is the reason that GNSS is a term that's sort of replacing GPS. Originally, GPS referred only to the US system. GNSS is a more generic term. I'm going to say GPS throughout this talk, and I really mean GNSS, but GPS is a lot easier to say. So how does it work? How do the satellites tell us where we are? We've got someone on the ground and we've got satellites overhead in the sky. And basically it works with ranging. The unit on the ground finds the distance between itself and the satellites that it can receive signals from. The signals are radio signals. They're traveling at the speed of light. And so using the speed of light, we're able to tell how far away we are. The way that actually works is pretty neat. Each satellite in the constellation is transmitting a different code. And the receiver knows all those codes and is so it's kind of as if the satellite is singing a song. I don't know what song, it could be anything. It could be Baby Shark or Old Lang Syne or anything. But the satellites are each singing a song, and the GPS receiver has that song in its memory as well. And they know nominally when the song started. And so the GPS receiver, as it receives signals from the satellite, looks at the incoming code or song and looks at the time gap between what it's hearing and where it is currently in its singing of the song. And it uses that time gap to measure the distance. Another way to look at it is we've got a receiver on the ground and each one of these satellites is singing its song or sending a code of ones and zeros. And the receiver is going to try to match up its songs that it knows and that it's kind of singing simultaneously to itself to the songs of each satellite. And when it finds one that matches, then it's going to say, okay, they're shifted by a few seconds. And that's because it's the delay between the time that it took for the song to travel from the satellite to the receiver that we're measuring. So because we know that the distance is equal to speed times time, and we know the speed of light, we're able to calculate how far away each satellite is from the receiver based on the time lag of the song that is received from it. So in sort of geometric terms, what this means is if we only have one satellite we can hear, then it means our position must be somewhere on the face of a sphere. And it's 2D in this picture as a circle, but picture it in 3 dimensions. We're on the face of a sphere that is equidistant from that satellite, whatever distance we measured. If we have 2 satellites, then we're actually on some kind of a circle, which is the intersection of 2 spheres. We're somewhere on that circle, but we don't know exactly where. Now, if we get 3 satellites, it would seem that we would have narrowed it down to a single point. And technically that's true, but the problem is that while those clocks of our receiver and our satellites are supposed to be exactly in sync so that we can calculate that time difference very accurately, there's actually a little bit of slop there. There's a little bit of clock lag between the receiver and the satellites. And so with that uncertainty in there, we really don't have the intersection of 3 spheres. So what we can do is get another satellite in the mix. And so if we have 4 satellites, the 4th satellite allows us to resolve the clock difference. And then using speed of light, we can calculate our exact position on the Earth. The math to that is here. Basically, what we do is we come up with a solution based on 3 satellites. We come up with a range to that 4th satellite, and there will be a difference between those 2 solutions, and we're able to figure out the clock offset by comparing those. Once we have the clock offset resolved, we can then position ourselves on the surface of the Earth quite accurately. When I say quite accurately, but there are a number of things that can mess with that accuracy. Obstructions, so if things get in between us and a satellite, multipath, and atmospheric delay. So obviously, if we have a hill or tree or other object getting in between us and satellites, that's going to affect our reception of the signal. and can possibly affect our accuracy by making us lose that satellite or by degrading the quality of the signal from that satellite. Multipath is when the signals from the satellites, instead of being received directly by the receiver with nothing in between, they bounce off of objects, the ground, buildings, trees, any sort of object. And so we get a bounce from the object to our antenna. And so the path that the signal has traveled is not a straight line anymore. And so since it's not a straight line, it's actually a longer distance between the receiver and the satellite. And we're going to calculate an erroneous position because we're going to calculate a farther distance than we should have because the time elapsed will be longer. Atmospheric delay is where, as GPS signals pass through the atmosphere, and that's the ionosphere and the troposphere, they tend to refract and slow down, therefore, because they travel longer distances than straight lines. And therefore, we get some uncertainty purely based on interference with the satellite signal caused by the layers of the atmosphere and refraction as the signal travels through them. So some ways around this, and the way that we really get high quality GPS positions are to use differential GPS. And the differential in differential GPS means that we use the difference between two positions to figure out where we really are. So the concept here is that we have two receivers tracking the same signals and errors from the satellites at the same time. We have a rover that's traveling along, trying to figure out its position based on satellites. And it's getting positions, but they're probably wrong by some amount. They're probably not quite right because of some of the error sources that we just discussed. But we also have a base station, and the base station is on a known location. It knows exactly where it is. We've put it over a place that we know the coordinates of, and we've told the base station what its coordinates are. So it knows exactly where it is, but it's still asking the satellite, it's still looking at the satellite and saying, let's see what happens if I calculate my position based on the satellites. And it gets also, a lot of the time, a wrong position. But since it knows exactly where it is, it knows how that position is wrong. It knows the direction and distance that the error takes form. So it's able to figure out what correction needs to be applied to the erroneous position to give it its real position. And if it can communicate that, either in real time or in a post-processing mechanism, if we can use that to adjust the position of the rover, then we can fix the rover's position and we'll know exactly where the rover is with much less error. So the idea is that we have a station on a known position that calculates the offset between the calculated positions and its known position, and then we use those either logged and then after the fact, or in real time we communicate those to the unit that needs to know where it is. And you can see that if we use these techniques, we can get rid of the vast majority of the errors due to clock offsets, miscalculations in the orbit errors, the ionospheric and tropospheric interference. We can do much, much better with differential GPS if we use differential GPS than we can with autonomous GPS. It's worth mentioning that where the satellites are in the sky is also going to be a factor in how good the signal to noise ratio or how the quality of the signal from the satellites. Satellites that are lower on the horizon are going to go through more of the ionosphere and troposphere, and so they're going to be affected more by those sources of error. So it boils down to, depending on our correction method, we can expect different qualities of position. If we're autonomous, like the GPS in your phone or the low-end sort of Garmin unit that you have, we're going to get probably better than 15 meters of our precision. It's better than that most of the time. It's probably 5 to 10 meters most of the time, but it can be worse. If we go to a real-time differential GPS solution, including satellite-based systems like SBAS or WAS, we can get as good as 1 to 5 meters. And if we get admittedly more expensive, but a more advanced GPS unit with real-time kinematic corrections, we can do sub-meter down to probably a centimeter or so. In terms of, those are all real-time solutions. In terms of post-processing or after-the-fact solutions, if we don't really care about knowing exactly to very high confidence where we are in real time, but we do need to know after the fact in order to process our drone data, then we can deal with post-processing, and we can use either post-process code differential, which is going to give us sub-meter or down in the low 1 to 2 meter accuracies, or we can use post-process kinematic or PPK, and again reach the sort of precision that an RTK, a real-time system, can give us, or maybe even better. I spoke a little bit about satellite geometry before, and this is relevant to all of those cases. The better the constellation, the better the quality of the constellation, meaning that you have more satellites and you have them in more parts of the sky, including straight overhead and not too low on the horizon, but basically spread across your entire sky above you, is a much better situation than when they are clustered all together or very, very near the horizon, or even worse, both of those conditions. So there are tools that we can use for planning when we go out to do our survey or our mapping, and it behooves us to, especially if it's a faraway place that it's going to take a lot of effort to get to, and we're going to lug a bunch of gear, and we're going to only be able to get there at one time, and we have to catch the conditions at this one time. It's a good idea for us to look ahead and, if we can, do a reconnaissance of the site, as well as use a satellite tool, a satellite prediction tool, to make sure that we're not going to have bad satellite geometry when we go out there, because it's the worst thing in the world, as everybody knows, to get into the field with all that effort and then find out that you can't get the data that you need. So that was a lot about how GPS works, and everybody probably needs a break about now. So let's take a quick break and then come back and talk about more about accuracy and precision and how to achieve them with our drone mapping efforts. So, welcome back. We're going to talk about accuracy and precision next. These are two terms that are often used interchangeably, and I'm probably even guilty of using one or the other through the first half of this talk, perhaps when I should have used the other one. But accuracy and precision are not the same thing, and it's a good idea for us to just think about what those two words mean. Anybody who's taken a statistics course or done science has probably seen this sort of graphical sort of metaphor for accuracy and precision. Accuracy refers to how close to the true value our value that we generate by measuring something is. So if there is a true value, accuracy is how close we got to it. Precision is to do with repeatability. So precision is if we measure the same thing 4 or 5 times, do we get the same answer all those times? Now, obviously, the best case scenario is to be both accurate and precise. That is, we get the right answer every time we measure. That's sort of, that's what we'd like to have. The next best situation, there's two actually that are both in some ways next desirable. If we're not accurate but precise, that is, our measurements are very consistent, but they're not right, and we can find a shift to move them to be right if we know the offset between truth and what our measurement gives us, and our measurements are very precise, all we have to do is figure out what that calibration factor or shift is. If we're accurate but not precise, that means our measurements are kind of all over the place in terms of they're not consistent, but they're all around the right value. They all are going to surround the right value. Then we can often use an average to find the right value if we have enough measurements, if we're accurate and precise. Now, if we're not accurate and we're not precise, then all bets are off, basically. We're not going to be able to use a systematic way of getting to the truth from our measurements if we're just throwing darts blindly at the board. So accuracy is often used when talking about GPS systems or positioning systems. A lot of the time the word accuracy is used, and I tend to shy away from that because a lot of the time we don't really know the real coordinate, and our means for knowing the real coordinate may be elusive or unavailable. And so a lot of the time what we're most concerned with is precision when we're mapping. We want things to be repeatable. It turns out that when you get down to the very fine scale and you're getting repeatabilities that are on the order of centimeters, and you're doing long-term mapping projects where you're comparing data from now to that collected 10 years ago, and you're in a place like California, things are moving anyway. So what the true coordinate of a feature is or a location is actually changes through time. And so it's really kind of that precision is the most important thing for us as opposed to absolute accuracy. Now, when you go out and you look at the vendors' specifications for various GPS systems, they're going to tell you, oh, it's accurate to, and they're going to use the word accurate. They're almost never going to say precision. They're going to say it's accurate to 1 meter, or it's accurate to 2 centimeters. And what you have to be careful with a little bit is what value they're actually quoting you. There's different measures that can be applied to describing accuracy or confidence. And oftentimes vendors will use the one that is most favorable to them. So circular error probable is the most forgiving of the accuracy measures that most GPS units will quote. That means that 50% of the positions are going to fall within that circle of that radius. It doesn't mean that all positions are that bad, but it means that 50% of the time this unit is going to give you a position that is within that distance from the true position. RMS is the next one, and that's root mean square, which means that 63 to 68% of the positions are going to be within that circle. And then 2D RMS is 2 times the distance of RMS, and that encompasses 95 to 98% of the positions are all going to fall within that circle. So given the same number, say ½ meter, if someone says my GPS unit is capable of ½ meter accuracy, and you say, well, what measure of accuracy are you using? And they say CEP, that is not as good as a unit that quotes the same level of accuracy at 0.5 meters, but they say that's the 2D RMS error. is ½ meter. You're much better off given at a given level of accuracy quoted with something that is a 2D RMS error of that much as opposed to the CEP. So we know that we need good GPS, and we know that if we use differential GPS, it gives us better positions, and that will translate to higher precision mapping products. So how do we achieve that? Well, one way is to put better GPS on our aircraft, and that means that when we fly, all our images will be geotagged with higher precision positions. And as long as the photogrammetry software knows that and takes advantage of those higher confidence positions and treats them accordingly, then we'll get better mapping product. The other is, and this is not exclusive, we can do both, is to use high quality or high precision GPS to get our positions for our ground control points. So let's look at both of those. There are a number now, and increasingly affordable, although they're still not on the cheap end of the drone sort of price scale. There are a number of aircraft now available with RTK and or PPK capable GPS systems on board included. These include the DJI Phantom 4 RTK, which as you might have seen in the equipment roundup is basically just a Phantom 4 V2 with RTK GPS, and it's that little sort of top hat thing sticking up from the top that looks a little different than our normal Phantom. That's where that GPS antenna is. The M210 RTK is an enterprise level DJI rotary wing aircraft that also has RTK capabilities. There are fixed wings with RTK, such as the EB, the Bird's Eye View Firefly, and the Trinity F90. Wingtra makes one, that's a VTOL. So there are a number of aircraft that you can buy off the shelf that include RTK GPS capability. Some of those vendors also sell a GPS, an RTK GPS base station that can go with it, that can communicate with the aircraft and transmit corrections to it. And some of them you're on your own in terms of that, or they're intended to use more PPK, which is an after-the-fact post-processing methodology. When it comes to ground control points, the best way we can make our mapping efforts more precise and better 3D models and better orthomosaics is to geolocate our products using ground control points. And typically for ground control points, we use conspicuous and identifiable features in our study area, and most of the time those are things that we put out ourselves. They can be permanent, but usually people put out temporary targets that the aircraft is going to be able to see. They need to be visible. They need to stand out from the background, high contrast, and they need to have an easily identifiable center point. That's the point for which we're going to get a good GPS position, and that's what we're going to tell the software. We're going to tell it this position is this exact coordinates. We need to pick the size appropriate for the scale and the ground sampling distance of our imagery. We need to take into account the optics of our camera and how high we're going to be flying, and make sure that we're going to get pictures that include our ground control points as clear as possible so that we can mark them easily in the imagery. A lot of people use fabric squares that they tack down the edges of. Those are easy to roll up and take with you. You can use tiles or pieces of plywood or 5-gallon bucket lids, all kinds of solutions to that problem. Often we use a checkerboard or an iron cross pattern that makes picking out the very center of it easy. Sometimes they're not black. Often they're black and white, but not always. Sometimes sometimes other colors are used. And the most important thing is that those need to be put out before you fly, because your aircraft needs to see them and take pictures of them. And then they can't be moved during the flight. And once the flight is completed and you have good positions for all of them, for the centers of all of them, then they can be picked up and moved. Occasionally, you'll run into a situation if your site is not protected from the public. You may run into a situation where people mess with your ground control points. We had a Good Samaritan clean one of ours up off the beach on her walk down the beach. Unbeknownst to us, we actually got pictures from the drone of her putting our ground control point in a garbage bag. That GCP did us no good. We weren't able to actually use it to map with, but it was kind of entertaining to see somebody doing the right thing and putting our garbage in her bag and taking it with her. There is at least one company, and there may be more now, marketing a line of smart ground control points. And this is very, very clever. I wish I had thought of it. They come in packs of 10. They are about a ½ meter on a side, square tiles that look like your average ground control point. But these have built into them an L1, L2 GPS receiver that's capable of logging data that will be able to be post-processed, kinematic processed. They have a solar panel and a battery, and basically you go to your site, you turn these things on, you throw them around in your study area in appropriate locations and leave them on, and they're logging GPS data the whole time once you turn them on. So normally on a survey, you put your GCPs out, and either before the flight or during or after the flight, you go around to each one with your GPS and you get a good position for its center. So if you've got a dozen of them or 10, then it could take, an hour or two to get all your positions. And if you want to make sure that you don't interfere with the flight and you don't want to be in the field of view of the aircraft, then you either do it before the flight or you wait till after. And it means it just extends the time that it takes for everything. These guys are logging the whole time, and they only really need 15 minutes of data. So your flight is probably going to be longer than that. And so when you're done, you land your aircraft, you go pick these things all up, turn them off, and download all their data by Wi-Fi. You send it off to the cloud, to the propeller aero processing service, and it gives you back a table of highly accurate, corrected PPK processed points. Sounds great. There are some downsides to it. You can only buy them in packs of 10. They cost about $8,000. The first year is free, but after that, an annual subscription is required in order to do the post-processing. They've sort of made it hard for you to post-process the data yourself. Further, these tiles sitting on the ground, the antenna geometry isn't really optimal. Multipath may be a problem. Satellite visibility may be a problem if there's any trees or bushes or other buildings or other obstacles around. An antenna on a pole at about head level or thereabouts is going to be able to see more satellites and get better quality satellite data than this thing sitting on the ground. But fact is, they work. They're proven they work. I have not used them myself, but I've talked to people who have, and they really do like them. Again, not cheap, but if time is money, then depending on how often you fly and how large of areas, these might be worth looking into. Oops. So we know we want to put out these targets and have them in our study area when we fly. What about how many do we need and where should we put them? So depending on your software, most software wants at least 3. It won't even use fewer than 3 ground control points. Probably something more like 5 is better. And for best practices, most people say maybe 5 to 10. Some people use the rule that they want to get, depending on the size of their study area, they are going to use a number of batteries to fly, and they say, well, we want to get 5 GCPs per battery. That's one rule that people use. So generally, the bigger the area, the more you're going to want, but 5 to 10 in a reasonable size area is a good ballpark. Now, where do you put them? You want them distributed throughout your study area, not clustered in any corner, not more on one side than the other. You want them in safe locations where they're not going to be molested or thrown away or covered by an incoming tide or have anything, or a car's not going to drive over them. And they need to be viewable from the sky. They need to be where your aircraft is going to be able to see them, and preferably you want each one, depending on your flight plan, to be visible in at least 5 overlapping images. They can't move, obviously, during your survey. And in terms of placing them over a USGS or other benchmark, that's a great thing to do, because you know with high confidence the position of that if you're able to get the coordinates for that benchmark. The fact is, though, that in any given drone mapping study area, there may be one or possibly none, no USGS benchmarks. If there's one there, put a target over it and make sure you put the center right over the center of the benchmark, and then you'll at least already have a position for that benchmark. But you're not going to be able to do that for all your targets, because they just don't put those benchmarks that close together. So you put your GCPs out, you do your flight, you come home, you got your images, and you've got your GPS data logger or your post-processed file that has your table of ground control point positions. How do you use them? You run the project processing, the photogrammetry through, for example, Pix4D is shown here, the same way you normally would, but you bring in the table of ground control points, and at that point you are going to have to specify, of course, the datum and the coordinate system that the ground control points are in. You run step 1, which is the initial processing in Pix4D. And when that is done, you're going to be able to go to the Ray cloud and mark the positions of the GCPs. After that, you re-optimize and you continue processing. So once again, you're going to, once you've got the project created and the images imported, you're going to import a text file of GCP coordinates. You're going to do initial processing. And then you're going to, in the Ray cloud, find those targets in the pictures from your aircraft and mark the exact center of the target in the Ray Cloud editor to tell the software, this pixel is this coordinate that I've already told you for this particular GCP. You want to try to mark each GCP in at least 5 and up to 10 images. After that, the benefits kind of diminish. So you want to do 5 to 10 images per ground control point. As you're going, you're looking at the error reported in the Ray Cloud editor, and you're going to monitor that. And if something starts going screwy, if you start getting bigger and bigger errors instead of smaller and smaller errors, you may want to either redo or throw out some of your marks that you've made on your GCPs. After you're happy with the way things have gone and you've marked at least 5 images for every ground control point, you re-optimize the project and you take a look at the results both there and in the quality report. And if you're happy with things, then you proceed with creating the rest of the mapping products and doing this processing steps 2 and 3. So looking at the quality report, you're going to see that for each ground control point, you have an estimated accuracy, which is what you told the software was going to be the quality of those GCPs coming in, and then a calculated error for each one of them in X, Y, and Z, then the software is going to calculate a mean, standard deviation, and an RMSE, root mean squared error, for each, for the all four or however many ground control points you had. So in this case, you see our overall error was about 2 centimeters in the horizontal, and even better than that, less than a millimeter, or in the less than a centimeter in terms of vertical error. I'm not sure if I believe that, but that's what the software says. Now, it's also a good idea to do some checkpoints if you can't afford it in terms of time and effort. The difference between ground control points and checkpoints are that ground control points are actually used to anchor and georeference the entire project, whereas checkpoints are used as just an independent measure of how accurate your results are. The positions that you tell the software for the checkpoints, you never mark the checkpoints, or you mark the checkpoints in the images, but the software never tries to make that pixel fit that position. It just tells you how far from that position that pixel actually is according to the model. So a checkpoint is used for an independent accuracy assessment as opposed to the ground control points, which are used to actually fit the model and georeference and fit the model. It's actually the case that if you're flying an RTK aircraft, you could probably get away with just 1 or 2 GCPs and a couple of checkpoints, and use them, and often you just end up using them all as checkpoints. But the idea is that your data are initially precise enough and accurate enough that you don't necessarily need the GCPs to tie it down, and you can use most of the positions that you have as checkpoints to assess your accuracy. So let's talk about GPS equipment and what works and what doesn't, and what to think about when shopping. Autonomous GPS is just really not going to do us much good in terms of improving our results. In fact, if we get our positions for our ground control points using autonomous GPS and give that to the software, we may actually make things worse instead of better. So we need DGPS capable units, and the sort of entry level of that are units that can do SBAS or WAS, wide area augmentation. Those are differential corrections provided by satellite, which can cut our error down to 1 meter or 2, or in some cases even half a meter. If we want to get to centimeter precision, we're going to have to use RTK or PPK. So just to refresh your memory, the difference between these things, autonomous is just what it sounds like. It's on its own. Positions are solved by the aircraft, the rover, and used as is with all the errors that come with it. The post-process kinematic means that we have a higher grade GPS receiver in our aircraft. It's able to receive more data from the satellites than a typical receiver. It's able to receive L1 and L2 channels, and it logs those positions. And we also are logging those positions, or someone is logging those positions at a base station at a known location. And we're able to access those log data somehow over the internet, or somehow we get those log data from the base station, pair them up with our rover's data, and we're able to come up with a post-process kinematic solution that is highly accurate. Real-time kinematic is kind of the same idea, but those corrections are actually transmitted to the rover in real time, so that the position solutions it gets as it's flying and taking pictures and tagging them are the corrected positions. So really the difference between PPK and RTK are the real-time versus the post-process aspect of it. So the higher precision GPS obviously are going to cost more. If we want fast, highly accurate data, RTK is going to be the solution we need if we need it in real time. We can set our base station, we can set up our own base station over a known point, or we can use NTRIP connections, corrections, it says connections, if the internet is available. I'll tell you what NTRIP is in a minute, but the point is that to do RTK, we need a source, as we saw here, we need a source of corrections in real time. And so our receiver, either we're going to have two receivers, one which we put over a known point, and we're going to broadcast our corrections to our roving receiver, or we're going to get corrections from somewhere on the internet from a nearby base station to do our real-time corrections. There are dedicated data loggers that we can buy that have a computer and the GPS and the ability to log the data all built into a handheld unit. And then there are an increasing proliferation of bring your own device type units where it's basically just a GPS antenna and small computer in a box or in a little compact unit that can communicate with an external computer like a mobile device, a phone, a tablet, or a laptop via Bluetooth or wireless, and the data logging is actually done on, and the controlling of the unit is done on the device. When you're trying to measure very accurately the position of the center of your GCPs, it's actually best to have a unit with a pole and either a tripod or a pole with a level on it that we can tell when it's straight up, so that we can put it exactly on the center of that target and hold it perfectly vertically to get our position. Obviously, we're going to have to take into account the offset of the pole height, but that will give us a better position than often a handheld unit that has a sort of ambiguous antenna embedded in it that we have to kind of hold over what we think is the point that we want. Here's a small bring your own device solution that we've just started playing with here at CCUMB. It's made by a company called Bad Elf. It's a Bluetooth unit that can talk to an Android or an iOS device. You can run ArcGIS collector or other software apps on that device to talk to the Bad Elf and get its positions. It has SBAS, and they claim as good as a meter in real time in good areas where SBAS is working well with something they call PPK processing built in. You notice down here, here's a plot of their supposed accuracy, and they're listing both, at least they tell us what they are, they're listing both the CEP and the 2D RMS, and you'll see that as you would expect, if all they told you was the CEP and they didn't tell you it was CEP and you thought it was 2D RMS, you'd be thinking it was a much better unit than it is. So the point is that just always pay attention to what it is that they're telling you, the accuracy, what that number supposedly is. Comes with or you can buy it with a pole. Anyway, they're actually even usable for PPK by logging Rhinex data. And the best thing about them so far, I think, is that they are very affordable. They're only about $600. The next most affordable GPS system that's like sort of RTK quality capable that I know of is going to be the MLID Reach 2. These are about $700 or $800, I think, and are very nice units for quite a good price. Fully RTK capable, wireless, Bluetooth, yeah. If you don't care about real time, and PPK is the way you want to go. You can actually get away with using some older units that were intended to, they're RTK capable units, but they're only able to be used with an external radio for the source of, they're not Bluetooth or wireless. This is from before those technologies, but they still can log data that is RTK or PPK processable. So an older unit like a Trimble 5700, I think I've seen these on eBay for like 150 bucks these days. It can be an option. The downside to that is that you have to log about 15 minutes worth of data at each GCP in order to PPK process. You can post-process using an online service called Opus, online positioning user service, something like that, or acquire data from the CORS network, which is continually operating reference stations, which are always logging. You obviously want to pick a station that's nearby you. We'll talk about that in a minute. But in any event, some of these older GPS units that can't take real-time corrections via NTRIP can still be used for PPK. So I've said NTRIP a lot of time, many times, and let's nail down what it is. NTRIP stands for Networked Transport of RTCM via Internet Protocol. RTCM stands for Radio Technical Commission for Maritime Services. It's a standards organization. So basically NTRIP is a protocol for streaming differential corrections, different DGPS corrections data over the internet in accordance to the specifications published by RTCM. You can set up your own NTRIP caster and open it up to the world or just your own users. You basically need a base station on a known location that's connected to the internet, and you can provide NTRIP corrections to yourself and your group or the world. There are some free and some paid subscription services available on the internet. One that's great here in California is CRTN, the California Real-Time Network. It's run by SOPAC, the folks at Scripps. They give free memberships to academic institutions. They've got something like 700 stations all up and down California. And the reason that's important is that for this to work, the reason the differential GPS works is that the base station needs to be nearby. It needs to be experiencing the same sorts of atmospheric and other interference problems as your receiver, so that the corrections that it's generating are valid for that receiver. And so 10 kilometers is probably, you want to be within 10 kilometers if you can. If you have to, you can push that out to 20 without too much loss of accuracy. But in any event, you want your source of corrections, whether it's real time or post-processed, you want your source of corrections to be as near to your study area and your actually sampled data as possible. Trimble RTX is another service that does post-processing, but it costs money. So, in summary, we don't always need high precision, but when we want to do repeat surveys, when we want to do change detection and other comparative studies, we want to minimize the error, and we want to make sure that any differences we're seeing from time 0 to time 1 are real differences. We want to plan our time out in the field for a time when GPS conditions are good. If we want sort of, quote, survey grade accuracy, and you've noticed I've probably, you may have noticed I've stayed away from saying what is survey grade accuracy or using any kind of standard. Means different things to different people. There is no one exact tolerance that you can quote. But if you want higher accuracy and precision, RTK and PPK are the best ways to get there. And unless your aircraft is equipped with those kind of with that kind of GPS gear, you will definitely need to use ground control points, and you should probably use them anyway, even if you do have an RTK aircraft. GCP, all these factors are important in how we make, place, and record the data from the positions from our GCPs. And we want to choose GPS equipment with our precision requirements in mind. Hope this has been helpful. I hope it's kind of got you thinking about the ways that you can get better and more precise mapping products out of your aircraft than you can just by going out and flying and coming home with a bunch of pictures. I'd be happy to take questions via email or otherwise. My information, I guess I should have put it on the slide. My information is in the instructor's information for DroneCamp, and I hope everybody had a great DroneCamp, and see you next year, if not before. Thank you.